So in this section, multi-core programming, we're basically going to go over just the high-level concepts of multi-threaded processes, right? How does a program work when we have this kind of knowledge that, hey, there's two things that may be happening in parallel? So let's take a look at some overall ideas here. So first of all, we want to kind of define some terms and be a little bit more precise than maybe we typically are. The terms I want to define are parallelism and concurrency. These are actually different things. Concurrency, well, the term we hear is parallelism, right? Parallelism actually means, I have maybe two threads, right? Picture T1 and T2. I always like naming stuff. Parallelism says that T1 and T2 are running at the exact same time, right? So maybe one's on one processor, one's on another processor, right? And they're doing things completely independently. Well, I mean, they have the option maybe of sending a message to one another, but for the most part, right, they're running simultaneously, right? This is parallelism. The other thing we have is concurrency. Concurrency is going to be something like, okay, I have thread 1 and thread 2. They're alive at the same time, but they're not necessarily running at the same time, right? So maybe I have one CPU, and that CPU is going round robin and saying, okay, thread 1, you get a second to run. Thread 2, you get a second to run. Thread 1, you have a second to run, right? They'll never actually be alive or running they'll never actually be running at the same time, right? Parallelism says they'll be actually running. Concurrency says they're not running. They're just existing, right? So they maybe be paused for a second, right? Later on, right, the other thread that's not running will get some CPU time and it'll go back, right? But they're not actually computing things at the exact same moment. So this is kind of our distinction between parallelism and concurrency. Now, for me, I think what we want to think about when we design stuff is concurrency, right? I shouldn't have to care how many CPUs my system has. What I want to do is I want to look at my problems and say, okay, I can figure out that there's this thing that can happen, this thing that can happen, and this thing that can happen, right? All these things are independent, and it's fair game for them to run in parallel. And so I'll throw them all into threads, right? Now, on a system when this goes to run, I don't really care what happens, right? Because if I do have the ability, right, to run different things at the same time, right, then I'm good to go, right? Those threads, right, 2 or 3, right, they can run in parallel. There's no kind of discussion about it. I've already set up or prepared my system to deal with that. But maybe it doesn't. Maybe I'm back to a single core system, in which case I can only run one thing at a time. Well, life is still good, right? I can certainly one run of those, one at a time. I make them all take turns, right? So if I'm building for concurrency, basically what I'm saying is we can scale to any type of system, whether we have one core or n cores, right? Just think about making things independent, right? And then somewhere, your operating system, your hardware maybe, is going to actually do the job, right, of taking your different threads and making sure that they're all, scheduled properly, right? Either running in parallel or they're taking their turns for concurrency, right? It's not our problem. We just want to enable it, right? So the system can do kind of the best it can in terms of optimizing things and running different things in parallel. Okay, so a note here, which is coming from, well, one of the sections the book has. The book talks about something called Amdahl's law. So basically the remark is this, and this goes back to maybe scalability, which we talked about for a little bit in the previous section. Parallelism isn't a magic bullet, right? We can't just add new threads and new threads and new threads, right? Maybe, and new CPUs under them, right? So they can run in parallel. We can't just add that, forever, right? And hope to get a program that runs instantly. It doesn't work like that. Generally, any particular program we have has two regions inside of it. It has a parallel region and then a serial region. Your serial region, right? That's the stuff that's obligated to kind of run in one monolithic block. We don't have the ability to say, divide this up, run this at the same time as something else, right? It's stuff that's obligated to be serial. Serial stuff may be something like, I got to actually set up my data and divide it into pieces before passing it to my threads, right? Some sort of preparation step. Or maybe at the end there's some sort of combination step where I'm pulling the threads, seeing, hey, what did you all do? And I need to combine that into one answer, right? Those are going to be kind of serial parts of your program. Then we have the parallel part. And the parallel part, right, as we add new CPUs to my system, right? Maybe if you have something like a supercomputer, that parallel part, right, is going to take less and less time, right? That's where I can get my speed up from adding extra CPUs. If you actually look down at the graph, right, on the lower right, it has a couple of different kind of curves. And you'll notice, right, as you move from left to right, what it's showing you is, hey, I'm adding more CPUs. And so in general, as I add more CPUs, I get kind of this faster and faster execution time. The problem is that I always have that serial region, right? Again, maybe it's preparing threads or destroying threads. That's always going to be there. And there's nothing I can do to speed it up, right? So my speed up is going to always be limited to how much of my code base is something that can be run in parallel, right? And so if you look at that picture, you'll see that graph kind of just flattens out, right? There are places where, okay, we've just added so many CPU cores, right, that's all I can do, right? That parallel region, right, is already supplied with as many cores as it could possibly take, right? I can't do anything better than that. And any additional cores simply don't help me. So again, right, the idea here, right, is that parallelism, it simply isn't an end-all, be-all. Unless maybe, right, there's this one special case here, right? Sometimes they have problems called embarrassingly parallel program problems, which are problems which are basically, they have no serial region. They're just all parallel stuff. Sometimes you see problems like that in data analysis, where you have just like a ton of different test sets or data sets, right? And you do an analysis on each of them, and those analyses don't really affect one another. Well, in that case, you really can do them all in parallel, right? And you don't need to worry about dividing things up because they already are divided up. Or you don't care about combining the result at the end. So there are a couple of problems that you can make all parallel, but in general, right, you always have that sequential region, and the sequential region is basically your bottleneck that says, okay, you're not going to get as much of a speed up as you would like, right, by adding a million cores. It's going to fall off at some point. Okay, so let's continue on to the next slide. So there are a lot of issues actually with taking a program and trying to create multiple threads. It's really not as easy as we would like. So a big thing, right, is simply to identify what are the tasks that we can make parallel, all right, that we can shove into a thread. Because the problem is my program, right, I see it as kind of being this monolithic thing, right, it's doing something. But then how do I figure out, maybe look at an algorithm and figure out, oh, there's this piece that can be run over here, and this piece that can be run over here, right? They don't really interact, right? They're somehow independent or separate regions in my program. It's really hard to identify that. It's hard to tell how things interact, mainly because we're not used to thinking about it. We just go and solve our problem, write our code. We don't really think about, how do I identify kind of horizontal pieces, right? We're used to thinking of functions, which are maybe vertical pieces, right? We're slicing our code, we have this, and this, and this, right? These are functions that run one after another. We never think about, I've written 2 lines. Is it fair game for those 2 lines to run at the same time, right? That's kind of a different mentality and something we don't really think about. Another big issue is balance, right? Imagine I create a bunch of threads, I give them a bunch of work, and then 3 of say 4 finish quickly, and then 1 is still running. This is no good, right? I'm being bottlenecked. Really, what I want is the ability to send out data that is kind of evenly distributed, so those threads all finish at the same time, right? Otherwise, I'm going to be held back. I'm not really going to be taking advantage of the fact that I could run these things in parallel, right? If I essentially have 3 processors idle while they're waiting on that 4th one, because the work wasn't evenly distributed. Another big issue. Another thing is data splitting. Sometimes it's just a question of, okay, I have these different threads. I know they're independent. I want them all to use this data though. How do I share that data out, right? How do I make sure that this thread has what it needs, this thread has also what it needs, right? It's hard for me sometimes to tell what should go where. Sometimes we end up just making a copy and saying, everybody gets their own copy of all the data, right? And then they can do whatever they want. 4th problem here, data dependency. So this is really kind of tying in with the first one, identifying tasks. Again, you have kind of these different things that happen in your program, and you have to ask yourself, which parts of my program are dependent on which other things, right? Because if if these particular lines of code need to, compute a result that another couple of lines are going to read, well then I need to make sure this happens first before this. And this is kind of an issue. Right? If I don't understand my data dependencies, well, I'm going to run my threads, and my threads maybe will lock out or wait around or stall, right? Because they're waiting for a result from somewhere else, right? And I didn't really think it through. So it's another big issue. Last issue, right, which is kind of, right, it's something we always worry about, right, is how do I test and debug stuff? Because in a normal program, right, a normal single thread program, I think to myself, okay, it's running, and if it crashes, basically there's one line somewhere where something went wrong, right? Maybe I put it into a debugger and I can jump to that line, I can look and see, this is the state of the program, this is what's happening, this was not happening, I need to update this or that. Fine. The problem is, right, multi-threaded, all of a sudden, it's not just, I have to worry about this one line, but then I have, another process or another thread, right, that's running in parallel. Well, what interaction happened, right? I have some, line 100 in the first thread run that, line 100, say, in the first thread is active, line 50 in the other thread is active, line 500 is active in the other one, right? And all of a sudden, I have these different kind of combinations, right? Because it could be one line from any of these programs, right? Well, it's the same program, but it's going to be kind of a different step, right? There's these different threads of execution that are happening, and I can be in different places at the same time. So it's like instead of trying to find that one needle in a haystack, right? Now I have to find 3 needles in the haystack because there's 3 different programs, right? 3 different places where my program could be active. I need to figure out what's going on, right? What is the interaction between all of those instead of just one? So this is something else that's kind of really, really tricky. Usually we just try our best to really make our threads super modular, right? So they're independent, right? They don't touch anything other than the input and the output. Usually that's what we try to do because it is very hard. especially on large systems, picture a supercomputer to debug so many interacting things. Okay, so another thing that we want to talk about here, parallelism types. So we have kind of two ways to split up work in general, right? Here, what first we're going to talk about is data parallelism. So maybe think back to when you took, either your CS2 class or your Intro to Algorithms class, and typically they cover something called merge sort. So merge sort is an algorithm, right, that is designed, to split data, to take a bunch of data, right, say picture an array, and sort it. The first step of that algorithm is to split it in half, right? So you're dividing your data. The algorithm goes, okay, sort the left side, sort the right side. Once you have two sorted sub-results, combine them back in, then you're done. This is actually kind of an example of data parallelism, right? Because we're saying, okay, I have this array that I want to sort. Say there's 100 things in it. Well, what I can do is I can split it into two smaller arrays that have 50 elements and 50 elements. And those now become subproblems that I need to sort, right? So you can imagine I could give one of those pieces to a thread and another piece to another thread. Both those threads can work independently to sort those two sides, and then later I put them together, right? So this is data parallelism, right? I'm taking my data, I'm dividing it into pieces so I can work on those pieces separately and then do something with that result later. Typically combine it, right? Or maybe I do some analysis, statistical analysis, whatever. This is one form of parallelism, right? If I can split up my data. Now there are other cases, right, where I can't actually split up my data, and basically my data is this monolithic thing, but then I want to have many kind of programs take that data and all do different things to it. So this is the idea of task parallelism. So for example, one thing I work on is kind of large-scale analysis of biological data, right? This is in terms of my research. And what we have there, right, is we have a lot of data, right? We have a lot of proteins, but we can't really split them in half because then we wouldn't have what we wanted, right? We would have half a protein, doesn't make sense. So we have this sort of task parallelism there where we say, okay, I want to perform the same analysis on the same input data, right, and the same protein. So I have, maybe 10 data analysis tools that run on each input, right? So the data isn't being split up there, right? Instead, there's some sort of duplication, right? Every single task, right, every single thread is getting that same data, and then from there, it's going and doing its own stuff, right, and producing some result. Then once we have that, right, we do some post-processing and analysis and stuff. Point is, this is kind of my second view, right? I can have my data be the same, and then what changes is my task, right? In the first case, right, our data was what changed, right? It got broken up, and then we perform the same task, right, the same thread on each of the subparts. So two different views here we have of parallelism. Both are valuable and apply kind of in different contexts.